Okay, now we've found in previous presentations how to find the derivative of the natural exponential function, and then we, of course, extended that with the chain rule. Now we want to find the derivative of its inverse, the derivative of the natural logarithmic function. Gang, before we do that, let me remind you. Probably one of the most important relationships when you study in Algebra 2 and pre-calculus, right? When you study exponential functions and logarithmic functions, you know they're inverses of each other. But we know that these two equations are equivalent. Okay, equivalent, of course, they're different in appearance, but we say that they're equivalent in value. They convey the same information just in different ways, okay? So here's what I want to do. Let's let the base b equal the natural number e. Okay, then that special relationship looks like this. Okay, see how that works? Now remember, gang, for logarithms of x base e, because that's so special, what we do is we use a different symbol for that. Remember, we use ln for natural logarithm. So I'm going to write like this. I'm going to say or. Okay, and I want to find the derivative of this natural logarithmic function. What is the derivative of ln of x? Well, what I'll do is, since these two equations are equivalent, let's start with the one on the right-hand side, okay? Take the derivative of both sides. Now, gang, listen, be careful. On the right-hand side, you have a composition. How do you know? How do you know that that exponent y is a function? Well, it says so right here. You see? So you've got a composition. That means when we take the derivative of the right-hand side, we're going to have to use the chain rule to do it. Okay, let me remind you. I'll use a different color. The derivative of e raised to a function is equal to itself times the derivative of its exponent. Okay, now we want to take the derivative of both sides of this equation. Okay, on the right-hand side, it'll just be the function itself times the derivative of the exponent. Okay, now divide both sides by e to the y. Okay, now at this point, I'm going to make two substitutions. Let me bring this down a bit. I'm going to make two substitutions. First, I know that e to the y and x are the same thing. So down in my equation, I'm going to say 1 over x. I also know that y is equal to the logarithm of x because it says so right here. So I'm going to replace the letter y, the function y, the variable if you like, with that symbol, on the right-hand side. Okay? So in other words, gang, the derivative of the natural logarithm of x is the reciprocal of x. Okay? The derivative of the natural log of x is the reciprocal of x. Said another way, the derivative of ln of x is 1 over x. Okay? And I'm going to say in general, all right, by the chain rule, we say one time for all time that the derivative of the natural logarithm of a function, let me make that g of x. Okay, this is an extension by the chain rule now. The derivative of the logarithm of g of x is the reciprocal of g of x times the derivative of g of x. Okay, it's a natural exponent or natural extension using the chain rule. So some examples. If I want to take the derivative of the natural logarithm okay, where the argument is x squared plus e to the x, well, the derivative of the logarithm of that argument is the reciprocal of that argument times the derivative of that argument. Remembering that the derivative of e to the x is simply itself. Okay, so I think, gang, what I'll do here is I'm going to use one of the old properties of logarithms and rewrite the expression like this. Okay, I can rewrite it again, can I? Got to blow off the dust, huh, of those 3 properties of logarithms going back to the old days, huh? All right, so the derivative, I can go term by term now. The derivative of the logarithm of x is 1 over x. The derivative of 3x is just 3. The natural log of e is just 1. Okay, so that's my final result right here. Okay, now here, notice that the base of the logarithm is not e. Okay, so that means so it seems we're at a bit of an impasse. But remember, we had alluded in a previous definition, or lecture rather, we had alluded to the change of base formula being pretty helpful in a different context, to be sure. We'll see that again. But for the moment, I'm going to use the change of base formula to rewrite this logarithm. Okay, that's the change of base. I haven't done any calculus yet. Next, I see that the logarithm of 8 in the denominator, that's a constant that I can just set aside. So now I'm going to take the derivative of the logarithm of 3x squared plus 5. Right? Okay, so according to the chain rule, the derivative of that logarithm of 3x squared plus 5 is the reciprocal of 3x squared plus 5. Times the derivative of 3x squared plus 5. And if you like, we can simplify that a little bit. It doesn't hurt. Okay, pretty clever, huh? How about this? See, now we mentioned something like this once before, didn't we? Right, so we can't take the derivative of 4 to the x because we don't know how to do derivatives of exponential functions to other bases. We do, however, know the derivative of the natural exponential function. Let's try this. Okay, let y equal 4 to the x. Then take the logarithm of both sides. Okay, I'm going to take the derivative of both sides. Now be careful, gang. On the left-hand side, you've got a composition where you didn't have one just a moment ago, right? You have the function y dropped inside of the logarithmic function ln. All right, so we've got a composition, which means that the chain rule is going to apply. On the right-hand side, notice I can write the logarithm of 4 to the x as x times the natural logarithm of 4. And the logarithm of 4, I don't know what that is. We could stick it in our calculator and find out, but it's a constant. Okay, now take the derivative of both sides. Chain rule on the left. So the derivative of the logarithm of y is the reciprocal of y times the derivative of y. On the right-hand side, the derivative of x times the constant ln4 is the constant ln4. Okay? Now multiply both sides by y to isolate the derivative. Okay? And it's customary, gang. You may recall that this is implicit differentiation, is actually what you're doing, right? It's implicit differentiation. To begin with, the letter y, see here? Notice that y is explicitly defined as 4 to the x. But as soon as we took the logarithm of both sides, now we have the logarithm of y. Now y is not explicitly stated, it's hidden, so to speak, behind the logarithm. It's implicitly defined, and so we use implicit differentiation. So you know that when you do that, it's customary at the end to replace the letter y with the function that it represents if it's available. And it is. It's right here. So this last equation becomes the following. Okay, so the derivative of 4 to the x is itself times the logarithm of its base. And we can generalize that, gang, one time for all time, but in a moment, or I'll do that in a moment rather. But let me show you another way, another method of solution, and then you can choose which one you like. Let y equal 4 to the x, and then rewrite 4 to the x this way. Okay, so what I'm using is the inverse properties of the natural exponential function and the natural logarithmic function, right? So said another way, it's kind of pedestrian, but we think of the e and the ln as canceling each other out. But we can rewrite the exponent this way. And so this implies then that the derivative of e to the x ln4 is itself times the derivative of its exponent. But what's the derivative of x times the constant ln4? It's the constant ln4. And of course, if we work backwards, if you like, we know that this expression right here is just simply 4 to the x. Okay, so two different ways of doing the problem. So I want to generalize. Let's say in general, one time for all time. The derivative of the exponential function a to the x is itself times the natural logarithm of its base. And by the chain rule, the derivative of a to a function is itself times the logarithm of its base times the derivative of the exponent. Okay, it's a natural extension of the chain rule. Okay? Okay, so here we have the derivative of the exponential function 7 to the sine of x. And by what we just figured out, that's going to be itself times the logarithm of its base times the derivative of the exponent. All right, now here you got to be careful again. This is an exponential function to be sure, because there's a variable expression in the exponent. But notice this time that the base is not constant. In fact, the base is a variable itself. Some authors refer to these kinds of functions as super exponential functions, okay? So for this one, I think we can use either method A or method B above the way that we approached the derivative of 4 to the x. You know, either one of these things. We can try either one of these approaches. You cannot, however, use this general statement. Okay, and the reason why is because in both these cases, the base A is a constant. Okay. All right, so I'm going to use method A, and I'm going to take the logarithm of both sides, okay? And the reason for this is so that on the right-hand side, I can bring that power down in front. See, that's one of the properties, a holdover, right? Remember there's 3 properties of logarithms back in our Algebra 2 and pre-calculus days. See, again, when you think about it, what was causing the problem in our function? It was the exponent. Well, now we don't have a problem with the exponent anymore because there isn't one. That was the whole idea in this case behind taking the logarithm of both sides. All right, now I'm going to take the derivative with respect to x, mindful that on the left-hand side we have a composition. So the derivative of the logarithm of y is the reciprocal of y times the derivative of y. On the right-hand side, use the product rule. So the derivative of the sine is the cosine. And the derivative of the logarithm of x is 1 over x. Okay? Multiply both sides by y to isolate the derivative. And then finally, as we mentioned before, right, when we do implicit differentiation, it's customary to replace the letter y with the function it represents if it's available, and it is. It's right here.